Exercise 3 will be about the comparison of public good provision in different kind of comparing different equilibria concepts. So what we will have in each of the sub exercises is that we have fixed preferences of three consumers, and then we will compare a situation where a government is maximizing a utilitarian social welfare function. Then we consider a game theoretical approach where we consider public good provision when individuals are behaving in a non-cooperative way. So we're considering the Nash equilibrium of some contribution game. And finally, in sub-exercise D, we will consider the Lindahl equilibrium of this economy, and we will compare the public good provision for those different types of equilibria concepts. So let's go briefly through the exercise description. So we will have three consumers, which are denoted by A, B, and C, and they have those quasi-linear utility functions that you can see here. ZA or ZB and ZC denotes the consumption of the private good for the respective consumer. And the second part is the utility of the public good that each consumer is deriving. Yes, so this is everything with respect to the utility function. Then the costs of providing the public good or producing the public good is equal to 1. So that's the marginal costs. And we have endowments in the economy, which are measured in units of the numeraire, and they're given by the values here. So in sub-exercise A, we are asked to characterize the level of public good of the Pareto efficient allocations in this economy. And this can be easily done by knowledge of proposition 1 that we proved before, because we know what must be fulfilled in order for an amount of the public good to be part of an Pareto efficient allocation, and that is the Samuelson condition. So we can get this part real quick. So what we know is that the following must hold: the sum of marginal utilities must be equal to the production cost, the unit production cost. So what we must have is Samuelson condition, which would say that the derivative of the utility of individual A with respect, so the marginal utility of individual A plus the marginal utility of individual B plus the marginal utility of individual C with respect to the public good should be equal to the production costs of the public good. And then what we get is the following: 1 divided by x plus 2 divided by x plus 5 divided by x. This should be equal to 1. And if we solve this for x, we get x is equal to 8. So what we can say is that an amount of the public good, which is part of a Pareto efficient allocation, is equal to, so the amount is equal to 8 if it is part of a Pareto efficient allocation. And we will use this kind of result to look into the kind of different, or to compare the different equilibrium concepts in the next sub exercises, and to see whether the solutions that we get there are yielding a Pareto efficient amount of the public good. So let us start sub exercise B. So in sub exercise B, we have the following. So we have a government, and this government is determining a level of the public good, which is maximizing utilitarian social welfare function. And if we're done with this, we are supposed to compare the level that we found for this, in this sub exercise with the Pareto efficient amount of the public good, which we determined in sub exercise A. So let's consider the optimization problem of the government, and this is given by the following. So the government is maximizing over the following. So the government is maximizing over the consumption of the private goods for all the consumers, so ZA to ZC. Then it's maximizing over the amount of the public good. And I will immediately write this in Lagrangian form, so we will have a Lagrangian multiplicator. So it's maximizing the social welfare function evaluated at the utility level of individual A, plus the same thing for B. So I'm just copying the utility functions of the individuals here, plus the same thing for individual C. So it's 5 times ln of x here. Plus, now we have a constraint, obviously. So the constraint is the sum of endowments, which is 100, minus the sum of consumption of the numeraire good for all individuals, minus the production cost of the private good. Okay, and this is the optimization problem of the government. And yeah, we'll just write an L here for the Lagrangian function. Yeah, and then the first order conditions are given by the following. So first, let's consider the derivative with respect to CA. Then what we get is the derivative of the social welfare function plus, so evaluated at the utility of individual A. This should be equal to lambda. So I already rearranged the terms here. Then the same thing for individual B. There we get the marginal utility, the marginal social utility evaluated at the utility of individual B should be lambda, and the same thing for individual C. There we get the following. This should also be equal to lambda. Finally, if we take the derivative with respect to the amount of the public good, what we get is the following. So we get psi prime ZA plus ln of x divided by x plus 2 times psi prime ZB plus 2 ln of x divided by x. Let me just make this a little bit smaller here. Plus 5 times psi prime ZC plus 5 times ln of x divided by x. This should be, here, let me also make this a little bit smaller here. And this should be equal to lambda. Finally, if we take the derivative with respect to lambda, we get that the budget constraint must be fulfilled with equality. Okay, so those are the first order conditions that we will have. And I will denote the expressions here. We'll denote the first order conditions by some numbers. So just that you know what I'm referring to when I'm solving the system here. So this will be inequality 1, this will be inequality 2, equality 3, 4, and 5. Good. The next thing that we will do is that we will simply substitute the following. So as you can see here, those marginal utilities here are equal to lambda, and they're also appearing here, here, and here. So what I will be doing is I will enter the right-hand sides of first order conditions 1 to 3 for the according expressions of the social marginal utilities in first order condition 4. And then what we will have is the following. So when you substitute, you get lambda divided by x plus 2 times lambda divided by x plus 5 times lambda divided by x. This should be equal to lambda. And if you solve this, you end up with x being equal to 8. And this is the solution. And now if you compare this with what we found out in sub-exercise A, you can indeed see that if the government is maximizing social welfare, so the amount of the public good in this optimization problem, so the solution of it, will be indeed Pareto efficient. Okay, let's go to sub-exercise C. So now we're considering a game theoretical approach and not a classical, more central governmental approach or like a social planner approach, but this is now a game theoretical approach. So now what we have is that the individuals are choosing their contribution to the public good in a non-cooperative way. So by xi, we now denote the individual contributions of the consumers to the total amount of the public good. So each of them is choosing their contribution to the contribution of the public good. And x is now the sum of the individual contributions for the individuals. And what we asked to is to determine the Nash equilibrium of this contribution game. And then we're supposed to ask, not supposed to ask, but we're supposed to compare the amount that we found here in the solution, so in the Nash equilibrium, with the amount that we found in questions A and B. And then we're doing like a simple comparative statics kind of exercise in that we're changing the endowments, and then we're asked to comment on what would happen with the equilibrium if there is this change. So let's go to sub-exercise C. And let us first of all write down the utilities of the individuals when they're contributing some amount, okay? So utilities of individuals when contributing some amount xi, which is larger than 0, so weakly larger than 0, and weakly smaller than their endowment. What we then have is that the utility of individual A, of course, depends on the amount of public good provision from himself and from the other individuals. So then what we have is 30 minus xa plus log of xa plus xb plus xc. The utility of individual B, and then we can also do the same thing for individual C down here. So this is given by 50, this is 20 here, minus xb minus xc plus, and then the only thing which changes here is the coefficient in front of the log. So we can simply copy this. So for individual B, the coefficient will be 2, and for C, it will be 5. Okay, and those are the utility functions of the individual in this contribution game, fixing some amount of public good provision, individual public good provision. So what we will do now is we will go through or we'll try to derive the best response functions for each of those individuals in order to determine the Nash equilibrium. So we will consider what is the best response of an individual given that the other individuals are behaving in a particular way. And we will do this for all three individuals. And finally, what we then get is, yeah, a Nash equilibrium if nobody has an incentive to deviate anymore. So then let's start with individual A. So individual A. So the first thing that we will derive is the marginal utility of individual A when he is increasing his provision to the public good. Okay, so what we will consider is the marginal utility when A is increasing his expenditure, to, his kind of provision to the public good. So this is then minus 1 plus 1 divided by xa plus xb plus xc. So this is the marginal utility of individual A when he's increasing xa. And what you can see is that this expression which you see is strictly negative if xa plus xb plus xc are smaller than 1. Sorry, if they're larger than 1. Okay, so if they're larger than 1, then the marginal utility is negative if A is increasing his utility. Therefore, his best response would always be equal to setting an amount of 0, or his contribution should be 0. And when is this the case? So this, his marginal utility, is strictly decreasing. Sorry, not his marginal utility is strictly increasing, but actually his utility is strictly increasing. So his utility is strictly decreasing if xb plus xc, if the sum of his rivals' contributions is larger than 1. If this is larger than 1, then increasing the amount of xa will yield a decrease in its utility. So the marginal utility is strictly negative here. Therefore, whenever xb plus xc are equally larger than 1, or is equally larger to 1, then the best response of individual A is to set an amount of the public good equal to 0. Yeah, so he will choose a contribution of 0. Because if he would choose a strictly positive amount, given that the sum of the rivals' contribution to the public good are weakly larger than 1, his utility would decrease, and yeah, this is not optimal. So he would have an incentive to deviate. So now, suppose that the sum of contributions of the rivals is strictly smaller than 1. Now the thing is that if this holds, then the issue that we have is that for some amount of xa, the marginal utility might be for sure strictly increasing. But if you take a look on the utility function, what you need to have is that the sum of the sum of the individual contributions should still be smaller than 1, because if it's not strictly smaller than 1, then the marginal utility would be decreasing. Sorry, the utility would be decreasing because the marginal utility is strictly negative. So the issue here is that even if individual A is choosing or can increase the utility in some interval by can increase the utility by some interval where it's choosing a strictly positive amount. The issue is that the utility, so the utility here, the utility here will be always strictly negative because the log of a number between 0 and 1 is always strictly negative. And then in addition, what you have is that, you have the costs of the public good, which are here. So this is then always -1. So the marginal cost of contributing a unit of the public good is -1, and then you end up with something which is negative. So what's the best thing that you can do? Well, the better thing that you can do is you can always choose an amount of public good equal to 0 instead of choosing a positive amount. Okay, so the solution here is that the problem is that if xb plus xc is smaller than 1 and xa is chosen such that xa plus xb plus xc is smaller than 1, the log of xa plus xb plus xc is strictly negative. Yeah, and therefore best response if xb plus xc is smaller than 1 is given by xa equal to 0. Okay, so to summarize, independent of independent of the contribution of the other individuals, individual A is always choosing an amount 0, which he contributes to the public good. And this is his best response. Okay, so if you want to have kind of a best response function, which we denote with some star, so xa star depending on xb and xc, this is equal to 0. So this is the full best response function that we have. So in terms of game theoretical language, what you would say is that for individual A, choosing a contribution of 0 is a strictly dominant strategy compared to anything else. So independent of what the other individuals are doing, his best response doesn't depend on what they're doing because he is always better off by choosing a contribution of the public good equal to 0 rather than choosing the strictly positive amount. So now that we know this, we can consider the other individuals. So now let's consider individual B. So let's consider the marginal utility of individual B. So we take the derivative of his utility with respect to his amount of the public good provision. This is -1 plus 2 divided by xa plus xb plus xc. And the thing is that B knows, so B knows that xa star is equal to 0. So of course B knows that for individual A, the strictly dominant strategy is given by choosing an amount of the public good equal to 0. Therefore, what we then have is that his marginal utility is given by -1 plus 2 divided by xb plus xc. Yeah, so this is all that he needs to care about. Now, let's consider the two cases which are interesting here. So if xb plus xc is strictly the sum of xp plus xc. If this is weakly larger than 2, then his marginal utility is negative. So his utility is decreasing if he's increasing his amount of the public good, or the amount of the public good that he provides. Therefore, whenever xc is weakly larger than 2, his best response is given by x b equal to 0. Okay, so whenever individual C is contributing an amount equal to 2 or larger, then individual B is better off by not providing anything to the public good, because his marginal utility of the additional good that he provides is strictly smaller than the cost that he has in order to provide this unit of the public good. Okay, now let's consider the other case. Now, 0 weakly smaller than xc, weakly or strictly smaller than 2. This is the next case that we will consider. So for this case, it must hold here. It must hold that xb plus xc is larger than 1, such that the log of xb plus xc is strictly positive. Yeah, because you would have the same issue as before. If the sum here would be if the sum would be smaller than 1, then the log would be negative, and hence for individual B would always be better off by choosing an amount 0. But as you can see here, if xc is smaller than 2, so for some range of the parameters, we can actually make sure that the sum is weakly larger than 1. So let me just check one thing real quick. Yes, okay. Good, so this is strictly positive. Now, how can we derive the best response of individual B? Well, this is done by solving kind of the marginal utility when we set it equal to 0. So let me denote the following. So derive best response. Derive response by solving the derivative of individual B, the marginal utility of individual B when he's increasing his provision of the public good, and this should be equal to 0. Of course, considering that individual A is choosing amount of the public good equal to 0. So then what we get is xb is equal to 2 minus xc. And as a consequence, the best response of B can be summarized in the following way. So the best response of individual B will only depend on the amount that C is choosing, and it will be equal to 0 if xc is weakly larger than 2, and it will be 2 minus xc if xc is strictly smaller than 2. And this is the best response of individual B. Now, next, we have to consider individual C. So for individual C, he also knows that XA star, so also knows that XA star is equal to 0. Now, what can we say here? So his marginal utility, when increasing his provision to the public good, is equal to -1 plus 5 divided by XB plus XC. And what you will have here is that if XB plus XC, if this is strictly larger than 5, then utility is decreasing. It's decreasing in XC. If XB plus XC is smaller or weakly smaller than 5, his utility is increasing. The marginal utility is strictly positive, and therefore his utility is increasing as long as he's choosing C in a way that, the sum of the individual contributions is weakly larger than 5. So this interval, his utility is strictly increasing in his contribution. So a consequence of this here, is that, let me erase this is a little bit confusing. So therefore, if XB is strictly or weakly, so it should be weakly here. If this is weakly larger than 5, then XC should be equal to 0. If XB is strictly smaller than 5, then what we can do is we can use the marginal utility and set it equal to 0. So what we have been doing for individual B, we do the same thing now for individual C. So we set this equal to 0. Therefore, what we have is that if you solve this, you end up with XC depending on XB. This is equal to 5 minus XB. So this would be the best response of individual C when XB is strictly smaller than 5. Therefore, what we have in a summary is the following best response. Best response of C would then be XC depending on XB equal to 0, then 5 minus XB if XB is weakly larger than 5. Here, 5 minus XB if XB is strictly smaller than 5. And this is the best response for individual C. And now all that we need to do is we need to find an intersection between the best response functions for individual B and individual C. So we don't need to care about individual A because his best response is simply given by choosing 0, independent of what the other individuals are doing. Actually, we can put away the parentheses here where we said that it depends on the contribution of the other individuals. So here it doesn't depend on the contribution of the other individuals, but here for individual B and for individual C it does. And the intersection, so let me change the color. Intersection of XB of XC and XC of XB is at XB star equal to 0 and XC star equal to 5. So you can draw this quite easily, and then you will see that the best response functions will intersect only at a tuple where B will choose an amount of 0 and C will choose an amount of 5. And as a consequence, so the Nash equilibrium will be the following. So XA star is equal to 0, XB star is equal to 0, and XC star is equal to 5. So only C contributes, and the consequence is that X star, so the sum of the individual contributions in the Nash equilibrium, is equal to 5. And this is the solution. This is the Nash equilibrium. So as you can see, only individual C is contributing, and the reason is simply given by the fact that individual C has the highest utility for the public good. Yeah, as you can see, all of them have the same costs. So each of them has marginal costs of 1 when producing the public good or when contributing to the public good. But C has actually the highest margin utility, and individual A and B are free riders basically now. Yeah, so since they have lower margin utility than individual C, they will free ride on the public good, and the consequence is an under provision of the public good, because what you see here is that the amount of public good, the total amount of the public good, which is provided here, is equal to 5. And this is obviously less than the Pareto efficient allocation, and also less than what we found out in sub-exercise B, where the government was acting as a social planner and trying to maximize social welfare. So you see, if you do not plan and optimize for the individuals, but when you consider a game which is non-cooperative and all of the individuals are choosing by themselves how much they want to contribute to the public good, so this is kind of a you might say that in real world, this is, in some circumstances, this is a more realistic approach. And you see that if this is the case, then there will be under provision of the public good. So we end up in a situation which is not Pareto efficient. So we could improve some of the individuals without making others worse off, starting from the point where we are in a Nash equilibrium. But we would need kind of a social planner or some other method to do this. Okay, so this brings us to the last sub-exercise. So sub-exercise D. Let me go back to the description. So here we are asked to determine the Lindahl equilibrium for the initial endowments, initial level of endowments. Sorry, I forgot one thing. So there was one part which I missed out here. So the last question in sub-exercise C was what would happen with the contributions if the endowments would change. And the answer is quite simple. Nothing would change because the utility functions are quasi-linear in the numeraire good. And this wouldn't change, it wouldn't change the marginal utilities of the individuals if you consider the first order conditions. And simply the expressions for the marginal utilities. So if you take the derivative with respect to the public good provision of the individuals in the utility functions, what you can see is that the endowment simply drops out. So the endowment would only come into play if one of the individuals wouldn't be able to provide as much of the public good that his first order condition would tell him to do, so in a Nash equilibrium. But this is not the case, because for all of the individuals, the Nash equilibrium is still feasible under this change in endowment. Yeah, so for individual A and B, nothing would change because they're simply providing 0 of the public good. And for individual C, there is a change in that his endowment is, it's still 20, I think. Yeah, so there is no change with respect to individual C. But as long as the endowment of individual C would be larger than 5, yeah, then he would still be able to contribute 5 units of the public good to the total amount of the public good, because then he would still be able to have be able to pay or produce this amount, because the production cost of the public good for him is equal to 1 for each unit. Okay, so then let's go to D. So we are asked to determine the Lindahl equilibrium for the initial level of endowments. And a Lindahl equilibrium is kind of an equilibrium concept where each of so the public good is not for free anymore, but it's costly to consume it. And the special thing here with the Lindahl equilibrium is that each consumer has kind of an individual price for consuming the public good. And the question is, what is the amount of public good provision if we consider a Lindahl equilibrium? And then next we are asked how this would change if the endowments are changed to the endowments which we have in sub-exercise C. Yeah, so the change there. Okay, let's go back. So we need some notation. So denote individual prices by PA, PB, and PC. And what we also need are Lagrangian multiplicators for each individual. So we have lambda A, lambda B, and lambda C. So we will go again. So we will start with individual A, then we will go to B, and then to C. So we start with individual A. His optimization problem is the following. He is maximizing over his consumption of the numeraire good, his public good provision, and the Lagrangian multiplicator. So the Lagrange function is equal to the following: CA plus log of XA plus lambda A times 30 minus ZA minus PA times XA. So one thing that I also forgot to mention is that now you can also control the amount of public good that an individual is consuming actually. So now we're considering a public good which to some extent is excludable. So you basically say that individual A can only consume as much of the public good as he actually is buying. And then depending on the demand, the public good is provided by the government. So that's somehow the way that it works. Now, given this optimization problem, we can write down the first order conditions. So I will numerate the first order conditions in the following way. So we'll numerate them with 1 to 3 for each of the individuals, and I will put an A here that you know that this is the first order condition for individual A. So here we take the derivative of the Lagrangian with respect to ZA. This is equal to the following: 1 minus lambda A should be equal to 0, and solving this gives us the following: lambda A star is equal to 1. Then we take the derivative with respect to the amount of the public good, which A is consuming. This is then 1 divided by XA minus lambda A times PA. This should be equal to 0, and solving this gives XA star is equal to 1 minus PA. And finally, we take the derivative of the Lagrangian function with respect to lambda A. What we get then is 30 minus ZA minus PA times XA should be equal to 0. Then if we substitute for XA with XA star here, what we get is ZA star is equal to 29 if we solve this. Now, what we have in the summary is XA star is equal to 1 divided by PA, and ZA star is equal to 29. So let us come to individual B. So individual B has the following optimization problem. He's maximizing over ZB, XB, and lambda B. And yeah, I forgot to enumerate here the first order conditions. Sorry, confusing everything. This should be A, of course. So yeah, back to individual B. He's maximizing the following objectives or function ZB plus 2 times log of Z XB plus lambda B times 50 minus ZB minus PB times XB. And then if you write down the first order conditions here, so we have the first one for B, the second one for B, the third one for B. So the steps are quite repetitive, so it's basically looking almost the same. So 1 minus lambda B should be equal to 0. Then we have lambda B star is equal to 1. Next, we take the derivative with respect to xb. This gives us 2 divided by xb minus lambda b times pb should be equal to 0. Now we know that lambda b star is equal to 1. Then we substitute it for lambda b here, and we end up with xb is equal to 2 divided by pb. And finally, if we take the derivative with respect to lambda b here, we have 50 minus zb minus pb times xb. This should be equal to 0. And then what we have is that we substitute for xb here with respect to xb star here, and we end up with zb star being equal to 48. Therefore, we have the following: xb star is equal to 2 divided by pb, and zb star is equal to 48. Then we come to the last optimization problem, which is for individual C. So now we consider individual C. So he is maximizing over ZC, XC, and lambda C. It's maximizing the Lagrangian function, which is then equal to ZC plus 5 times ln of XC plus lambda C times 20 minus ZC minus PC times XC. Then we have the first order conditions for individual C. Again, 3 of them. So consider first the derivative with respect to ZC, which gives us again 1 minus lambda C, supposed to be 0. This gives us lambda c star equal to 1. Then next, let me give a little bit more space here. So the derivative with respect to xc will give us 5 divided by xc minus lambda c times pc should be equal to 0. Plugging in for lambda c and solving for xc gives us xc star is equal to 5 divided by pc. And then finally, if we take the derivative with respect to the Lagrangian multiplicator, we have 20 minus zc minus pc times xc should be equal to 0. And then if we plug in for xc star and solve this for zc, we end up with zc star equal to 15. Therefore, what we have is xc star is equal to 5 divided by pc, and zc star is equal to 15. And this is all that we need in order to derive the Lindahl equilibrium, because if you take a closer look on the slides, what we have is that a Lindahl equilibrium must kind of fulfill, or the individual prices in the Lindahl equilibrium must fulfill two conditions. Okay, so Lindahl equilibrium must fulfill, so prices PA, PB, and PC must fulfill two conditions. So the first one is that the sum of the Lindahl prices must be equal to the costs of the public good, so the marginal cost of the public good, which is equal to 1 here in this model. This is a kind of the Samuelson condition, if you want to state it like this. Yeah, because if you take a close look on the first order conditions of all the individuals, the prices are always equal to the marginal utility of the individuals, and hence the individual prices are equal to the individual marginal utilities of the individuals, and hence the sum of Lindahl prices is actually equal to the sum of marginal utilities. And this should be equal to 1. And a consequence will be, and this is like already part of the solution, that the public good provision in the Lindahl equilibrium will be Pareto efficient. But yeah, we will see this later. The second condition is that all individuals are consuming the same amount of the public good. Okay, and this is also related to what we saw in proposition 1, in that there is no point in not like excluding individuals from the public good. So we are able to exclude them, but there is no reason in doing so if we are going to consider an allocation which will be Pareto efficient. Yeah. So if this condition 2 would be violated, the solution wouldn't be Pareto efficient. And the issue, no, not the issue, but the solution here is that what we do is we simply plug in for PA, PB, and PC. So solving the systems of equations with respect to PA, PB, and PC yields the following. PA star is equal to 1/8, PB star is equal to 1/4, and PC star is equal to 5 divided by 8. And a consequence of this is then that xa star is equal to xb star. This is equal to xc star, and this is equal to 8. So as you can see, the total amount of the public good that we are providing in the Lindau equilibrium is equal to 8, and the individuals will pay individual prices for the consumption, so different individual prices for consuming an amount 8 of the public good, but the prices will be higher the higher the marginal utility of the public good is. Yeah, so the idea is that if there is an individual who has a high marginal utility for the public good, his Lindau price will also be higher, and the prices will be chosen in a way that the Samuelson condition is fulfilled, and they will be chosen in a way that all of the individuals are consuming the same amount of the public good, so there is no exclusion of the public good because there would be no point in doing so. And this is basically the solution here. So as you can see, the Lindau equilibrium public good, the amount of public good provision in a Lindau equilibrium is Pareto efficient because it's equal to what we found out in sub-exercise A. And there was the last question, what would change if we change the endowments of the individuals. So I think the change was only with respect to individual A and B. And also for this case, there would be no change in the solution because everything is still, so the budget constraints of the individuals are still fulfilled. So this allocation would be still achievable under the new endowments, and hence there would be no change in individual prices here because the prices are depending on the marginal utilities and not really on the endowments of the individuals. And as long as the endowments are sufficiently high, there is like, if they're still high enough under such that the old allocation can be achieved, then it's still Pareto efficient, or it's still a Lindau equilibrium to choose this old allocation. Yeah, and this is basically the solution to the last question in sub exercise D. And yes, this was the last exercise. So also the last, this was the last sub exercise in this finishes problem set 2. Next week we will have a paper discussion, if I'm not mistaken. So I will talk about the actual Samuelson paper. And yes, if you have any questions, feel free to send me an email. And otherwise, see you next week.